All right. And the last thing we're going to be looking at is the application of vector equations to all the kinematic stuff that we've done. So that will look at speed, time, and velocity. Now, if you had your vector equation, where r is the position vector of any point on your line, and a is some point on your line, and b is your direction vector, and t is your scalar, what we're going to find is how we can apply this to speed, time, and velocity. So again, r is a position vector of any point on a path that an object is taking. So maybe a moving object is traveling in a straight line. Your a is a starting point of when that point is starting on that line, and t, the parameter, is going to be your time. Your vector b is going to be your velocity vector, and the length of b is going to be your speed. So let's just take a simple example. Let's say we have something starting at the point 1, 2. So we've got an object here, and it's traveling 2 to the right, and then 3 down.
To their lockers and clean everything out. Staff members, please supervise your homeroom groups at this time. Thank you very much.
So it's moving 2 to the right and 3 down. That's the velocity vector. The velocity vector is telling which direction it's going in, and if we figured out the length of this velocity vector, so here's our velocity vector, it's going to travel, if t is the time, say time in hours, in 1 hour it's going to travel 2 to the right and 3 down. The length of that vector, when we figure out the length of 2 squared plus negative 3 squared, square root of 13, that's going to be its speed, because that's how far it's going to travel in 1 hour. So if this was in kilometers, we would have square root of 13 kilometers per hour. So your velocity vector is this one right here, and the length of that velocity vector is telling the speed that it's going. So we've got a starting point. T is going to be in time, either in minutes or hours or seconds, and then that velocity vector, the direction vector, is going to tell you which direction it's going in and how far it's going to go in 1 hour. And once you find the length of that, you're going to get the speed of that object. So here we've got an object. It's got its starting point at 1, negative 1, and a velocity vector of 3, 4 in kilometers, and we're looking time in hours. So the velocity vector here will be the 3, 4. And if we find the length of that vector, a squared plus b squared equals c squared, we will get the speed to be 5 kilometers per hour. In other words, in 1 hour, it's going to travel from its starting point at 1, negative 1, it's going to travel 3 to the right and 4 up. And if you had this triangle, 3 to the right and 4 up, a squared plus b squared equals c squared, the length of that vector would be 5. And so the speed of that object, it's gone 5 kilometers in 1 hour. And so that's its speed, 5 kilometers per hour. Describe the motion of the object in words. It's traveling in the direction it's traveling in that direction of 3, 4 at a speed of 5 kilometers per hour. Now, if we wanted to write the equation of a line in y equals mx plus b, or in this case, ax plus by equals c, which is sort of just a rearrangement of y equals mx plus b, we could start with our original equation. Our vector equation is right here, 1, negative 1. So if we take our equation, from here you could write your parametric equations and then from your parametric equations you could get your Cartesian form by solving for t in both of them. And from your Cartesian form, since that no longer has t in it, could multiply both sides, sort of a cross multiply here, and rearrange it so you get the form that you want, which will be 4x minus 3y equals 7. And if you wanted to rearrange that to y equals mx plus b, you could do that as well. So again, this is just practicing taking something from vector equation and moving it back and forth between the parametric equations, which become very helpful if you're trying to find an intersection point, or switch it to the Cartesian form if you want to change it back to forms that you're used to using before. So I'm going to get you to try this one. I'm going to go check on my lockers. All right. How did you do finding your vector equation of a line from your parametric forms? The velocity vector will be that 5, negative 2. And if you do a squared plus b squared equals c squared, you'll get a speed of the square root of 29. Our units here are meters and our time is in seconds. There's a pole located at 39, negative 9. So if we look at our parametric equations, what we're wondering, is there a value of t when the x-coordinate's at 39? Is that same value of t going to be when the y-coordinate is at negative 9? So plugging into our parametric equations the 39 and solving for t, we're going to get t is equal to 7. And similarly, if we solve for t when we plug in negative 9 for y, we get t equals 7. So the answer is yes, it will collide with that pole at 7 seconds.
Would all students who have finished with their locker cleanup please return to their period 3 classes? If you finished with your locker cleanup, please go back to your period 3 class. Thank you.
So we have a jet flying at a speed of 700 kilometers per hour, and it's going in the direction of 2, 6, negative 3. So what we know is our velocity vector has to be in the same direction as this. But the problem is with 2, 6, negative 3, if we calculate the length of this, a squared plus b squared plus c squared, we're going to get that this vector has a length of 7. If it's traveling at a speed of 700 kilometers per hour, our velocity vector has to have a length of 700. So what would we have to do to this vector to make it have a length of 700? Well, this one you can probably do a shortcut. Since its length is 7, how much longer do you need to make it a length of 700? You would have to multiply this vector, let's call this vector u, 100 times longer. Does that make sense? and then it will have a length of 700. So it happened that there are nice numbers here. We can just take the vector that we have and multiply everything by 100 and get our velocity vector. And the length of that vector will have a length of 700. Now there might be some other times that it isn't a nice number. For example, if that jet was flying at a speed of 652 kilometers per hour, then there's not going to be something nice and easy that you can just see, oh, I need to multiply by this to get 652. Then it often makes sense to first find your unit vector with a length of 1. Can you see that the unit vector of this one would just have a 1/7 out in front? And then if you wanted 652, you could multiply your unit vector by 652, and that vector would have a length of 652. So we had a nice one that you could just multiply by 100, but it's good to remember that idea of I can find my unit vector and then multiply by that to get a vector of any length that I want. So here we have a yacht leaving a harbor. The harbor is at the origin, 0, 0. So at time 0, that yacht is right at the origin. There's a cargo ship that isn't at the harbor. It's starting at the point 6,3 at this same time that the yacht leaves. And so sometimes when we have two vector equations, you notice that we have two different parameters here. One's t and one's s. But if we're talking about a specific time for both ships, then the t would be the same. So at time 0, the one ship is at the harbor, and at time 0, the cargo ship is at 6,3. Find the speed of the yacht. 25 plus 64. Square root of 89. Everything here is in kilometers, and the time is in hours. Find the distance of the cargo ship from the harbor. So at time equals 0, the cargo ship was at 6,3. If you were figuring out the distance from 0, 0 to 6,3, again, you could just do a squared plus b squared. Root 45 kilometers. You could leave it like that, or if you wanted to, you could simplify that and write it as 3 root 5. If both of them continue on the same courses, would they collide? Again, any time that we're trying to find out if two paths cross, we're going to go to the parametric equations. So your parametric equations for the yacht were this. Your parametric equations for your cargo ship look like this. Now we can set those x coordinates together and solve for t. So if we do that with our x coordinates, notice you only have one variable here. So you can rearrange and solve and get t is equal to 3. But it's not enough just to solve for t with one of your coordinates, because they might be at the same x coordinate at 3 hours, but they may be at different y coordinates at that time. So we also have to see, does it happen that when you solve for t with the y coordinates, that you also get t equals 3? And in this case, you do. And so since there's a specific time where the x and the y coordinates are the same, we can say yes, they will collide at 3 hours. If we want to, we can even find the point by plugging in 3 at the point 1524. That's where they're going to crash together. So we've got a theme going here. First we hit a pole, now 2 boats have crashed. It's not looking good for the final day. So read through this one. And I'd like to see if you can figure out part A. Writing down the vector OP. So if it's initially right here at the point P, 31 kilometers west and 32 kilometers south, that vector OP would be minus 31 minus 32. Now, if you get questions like this, you're going to be very tempted to use this 1612 as part of what you want to show. Because this question says, show that the path of the ship can be represented by this equation. So we're basically trying to find the vector equation of the line. And any time that you use information that they want you to show, before you've showed it, you've kind of gone in a circle. You can't just say, well, since you told me this is the answer, I've showed it to you. That's not good enough. You're sort of going in a circle. So you need to take only the information that you know, and we want to write our vector equation of a line. What do we know? We know the ship is at negative 31, 32. So we could say for sure that that is a starting point for our line. We know that it's going in the direction, right? We're told that it's going in the direction of 4, 3. The direction is 4, 3 with a speed of 20 kilometers per hour. Now, if we find the length of 4, 3, right? We're going to find out that that has a length of 5. Our velocity vector then would need to be four times longer than that. Because if that has a length of 5, that's only traveling 5 kilometers per hour. We need a speed of 20 kilometers per hour. So if we would multiply this direction vector 4, 3 by 5, we would get 16, 12 as our velocity vector. And so now we can put that into the equation to solve for this. And that would be how to show that 1612 is the answer rather than using 1612 to show that it works. So it's not okay to say this works because if you figure out the length of 1612, its length is 20, and so that's the speed that it's going, so it works. You can't use the information they've given you to show that it works. You need to show that that is the right answer based on the information that you know. So we had our point P, and in 1 hour, it's going to go 16 to the right and 12 up. We've got our vector equation of our line starting at negative 31, negative 32. So at t equals 1, which is the point R, if we plug that in, we're going to get our position vector for the point R to be negative 15. Perfect. Thank you. Negative 15, negative 20. So that will be our position vector for R. If you want to find PR, well, you can either look at the diagram that's drawn there and figure it out. P to R is 16 to the right and 12 up. Or you could figure it out because if I wanted to go from P to R, I could go from P back to O and then go from O to R. Well, P back to O is negative 31 over negative 32. And O to R is negative 1520. If we put those together, we get 1612, which is exactly our velocity vector, which makes sense. Now, when the point reaches R, we want to show that this lighthouse first becomes visible. So we know that our point R was negative 15, negative 20. In fact, that's our position vector. If we figure out the length of OR, since the lighthouse is at the origin, that would tell us exactly how far away from the lighthouse it is. And the length of OR, a squared plus b squared equals c squared, is going to be 25. Since the lighthouse had a radius of 25 kilometers, it would be first visible at that point. So here's a second ship. Again, we notice that it's using the same variable t. Do you think they're going to collide? Well, again, anytime you're trying to find an intersection point, you'd set up your parametric equations. So from our first ship, we'd have those parametric equations. From this second ship, we'd have these equations. Setting our x values together and solving we would get 6t is equal to 24. So t is equal to 4. And then checking with our y values. Yes, 9t. So since they are at the same x coordinate and the same y coordinate at t equals 4, they will crash. Bang. Boom.